Welcome to the third edition of the Mphasis-Samvaad Talks and the first one online. Today we have with us Professor Dinesh Babu Jayagopi, who's going to give a talk on deep generative neural networks for multimedia generation. Dr. Dinesh Babu Jayagopi is currently an associate professor at IIIT Bangalore, where he heads the Multimodal Perception Lab. His research interests are in audio-visual signal processing, machine learning, and social computing. He obtained his doctorate from Ecole Polytechnic Federale Lausanne, EPFL, Switzerland in 2011. One of his papers published during his PhD on modeling dominance in group conversations using nonverbal activity cues in the IEEE transactions of audio, speech, and language processing is a very widely cited one. His work has won several recognitions in the form of Best Paper Awards. So we welcome Professor Dinesh. The stage is yours, Dinesh.
Thank you for the kind introduction, Jaya, and also thanks to the opportunity for me able to give this talk. So I'm sort of surprised there are around 300 participants already. So seems like the message. I mean, they're probably not on the in terms of the title. Title seems little easy to go. Multimodal synthesis using deep generative neural networks. But maybe people are curious about the sentence in the abstract, which is: can machines paint? Can machines write poems? Can machine take interviews? Right. So we'll address that in the talk as we go along. At the same time, I'll also like to mention that this will be a talk which is more along the lines of trends in applied machine learning, right? So we'd like to look at an interesting trend in applied machine learning. So we will be talking about, what is out there published and interesting work. And we will also talk about work that we have done in the lab and as an application of such deep generative neural networks. Okay, so it is going to be part general and also part which is our work. Okay, so let me get started. So the title reads Multimedia Synthesis Using Deep Generative Neural Network. And had this talk been given, say, 5 years back, we would have given a talk which looked something like this, right? Where we have multimedia analysis, not synthesis, analysis using deep discriminative neural network, right? So this used to be very popular between 2012 and 2015 and even now. But then what we will be talking about is more on the synthesis and also using generative neural networks. Okay, so before we get there, quickly, what is this about? Analysis and discriminative neural network. Analysis is about, given an image, video, or text, you want to find out something semantic about the image, video, or text. And for example, what is this object, right? Or what is the person doing? What part of speech is this word, and so on. And so this is the problem, right? So I have not talked about speech, but it applies equally to speech as well, right? Maybe what is the emotion that the person is expressing in the speech. So how are these problems solved, right? These problems could be solved and more contemporarily are solved using deep discriminative neural network, where a deep neural network could look like this. Image goes as input and out comes your answer, which is what is this object? So this could be an animal here, a dog, right? And you have multiple layers, which we can see here, multiple hidden layers. And if it is an image, we particularly employ what is called a convolutional neural network. A convolutional neural network basically does what is called a local weighted sum, right? And people also call it kernel. Maybe the first few layers extract interesting information about edges, blobs, and so on automatically. And whereas you have much more semantic information in the later part of the neural network, right? And as you can see, this is the feed forward or the forward operation. And there are enormous number of weights here to be learned. And a simple example is shown here, where you have a single hidden layer. And there are weights here as well as here, right? So there are weights to be learned, and these weights are learned using the training data, where you have we have the input output pair, and so input and output that is available. The model gives us output, which is f of x. You compare f of x and f of y, and using a loss function for every data sample, you can accumulate over multiple data samples, and you can back propagate and learn these weights, right? And this is what Jeff Hinton was quite famous for, which is a back propagation algorithm. But he's also famous for this ImageNet architecture. So this may not be particularly ImageNet, or which was used to do to build a deep discriminative neural network, right? To on the ImageNet data set, and that is called the AlexNet, right? But he was one of the primary author of this paper, right? So as you can also see, there are these convolution operations. There are also these max pooling operation, which is more like a downsampling operation, which makes the sort of the encoder. If we start to call this as an encoder, you start to go from larger size to smaller size, right? And you do a deep analysis and find out what the object is, or what is the semantic meaning of this image, right? And as we said, we are talking about multimedia synthesis using deep generative neural networks. And here we are addressing problems where we are generating image or generating video, text, and so on, right? And an example problem could be that you have, for this task, the input could be a blurred image, and you want to get as output a deblurred image, right? So you're essentially solving a image processing problem. Or you could also have another application where you're trying to generate a video, right? And there is a famous paper called Everybody Can Dance, where you have a video of an expert and a video of an amateur who just does some steps, but then you can create a video. People call it as a fake video, whatever, right? So you create an artificial video which doesn't exist, where the person who's an amateur, he dances, right? And he exactly dances the same steps as an expert, right? So this is another interesting application. You can call it video editing for as this, right? And you can also have another application where you're producing text as output, maybe an image inspired poetry generation, right? And you could also look at generating text where it could be a follow-up question generation in an interview. An interviewer asks a question, interviewee answers, and then the interviewer again asks a question, right? And that is sort of a follow-up question that is being generated, right? So these are interesting applications. We'll come to each one of them. And how do we do it? How do we address this task? By using deep generative neural network. And we will talk about two such networks: generative adversarial networks for image and video, and generative pre-trained transformers, which is for text. Okay, so so as we go along, we'll talk about each of them in detail. Okay, so the most crucial moment, I would think, in the image generation literature is where people solve the problem of image segmentation, where image goes as input, and you have to give out a semantic output which is the same size as the original image. Okay, and image goes as input, image comes as output. Half of it we know what it does, right? You do convolution. You take a linear combination of the input and do a summary or compression, right? Whereas here you have to do what is an expansion or interpolation. And instead of using some fixed weights to interpolate, you can also learn those weights, right? And you can learn to interpolate given enough amount of training data. And the beauty now is you take an image as input and give image as output, right? So which means that you can start to solve interesting problems, right? So you can deblur an image if you want, provided you have the pair of images where the output, so you can give as input a blurred image and an image which is not blurred, right? And if you can have mechanism where you can actually generate these pairs of data, right? Maybe you you record data at a high speed, right? And then generate these pairs of images where you have a ground truth image which is not blurred, and you have an image which is blurred, right? And you can train a network, and you have these weights, huge number of weights. You can learn using the same backpropagation algorithm, right? Of course, neural networks are a little hard to train. You have to have lots of tricks and so on, but still the essential principle remains the same, right? So it can be for image deblurring, for image super resolution, enhancement, and so on, right? Several problems that can be attacked using the same method, right? And one such method is what was published in 2017, which is a multi-scale CNN for deblurring, right? And as you can see, what you have are pair of images where you have the ground truth image as well as the blurred image, right? And from that, you can downsize and get these images which are on the left. You can also get these images which are on the extreme right. And now you start a network, right? You take the smallest image which is blurred, get it through the network, and produce an image like this, right? And you can also upsample and produce an image which is of double the size, and you can combine it with the image which is in the middle, right? Now you can again run through this network and produce this output, right? And what is interesting is when you so there is this forward architecture. There is also the back propagation where you compare these two columns and maybe at a pixel level, just look at the mean square error, and you will be able to back propagate and then learn these weights, right, to be able to do the deblurring, right? And here you see the rest block, which is one of the blocks here. Rest block, the intuition is you have an image X, and suppose you have already learned some pixels well, you don't have to waste your energy for those pixels, right? You can only focus on the pixels where you still haven't learned and try to model that, right? Whereas the X is already available for you, and you can use those pixel values, right? So it's a very interesting trick which was proposed in 2015, which is also a paper from Microsoft, right? Using the residual connection. Okay. So far, we have what we have talked about is to be able to build a generative model, right? And the generative model, thanks to this encoding and decoding, and you have the compression and decompression, interpolation. You can actually take image as input and image as output, right? So that part is ready now. You can generate images. So what was proposed was this adversarial loss, which is an additional loss along with the losses that usually are used, right? Mean square error and so on, right? So what is good about this loss? So it's a very nice image which shows the effectiveness of using adversarial loss. Suppose we are predicting, we are trying to predict the motion of this head, and this is the ground truth. From a previous frame, we are trying to predict this frame, and this is the ground truth. You see that the adversarial loss gives a much better image. So it's a much better sample compared to when you use mean square error, right? So mean square error, what it does is, it of course tries to predict what could be the next frame, but there are several possibilities. But then there is also this possibility of, I mean, just to hedge its bet in terms of doing well on the MSE, there is a possibility that it'll blur the image, right? Whereas adversarial loss helps you to get a much more cleaner image, right? Okay, so we're going to talk about GANs in little detail, and first we'll solve the problem of image generation, right? Using GANs, which means that we will be able to learn the syntax to begin with, how an image or valid image looks like. Then we will talk about conditional image generation, right? Where we can maybe give some input and then get an output, right? Maybe in the first case, it'll just be generate a image, right? That's the first problem we'll solve. Then we'll solve the problem of generate a image, which makes sense given this context image, right? So this is the input. So just a quick advertisement for GANs. We have seen Jeff Hinton, who was one of the Turing Award winner. And here you see there are two more winners as well, right? Yann LeCun and Yoshua Bengio. Yann LeCun famous for CNNs, and Yoshua Bengio famous for RNN and text much more than images, right? And Yann LeCun, who is a director, AI research director of Facebook, he calls adversarial training the most interesting idea in the last 10 years in ML, right? So that's a lot of advertisement for Ian Goodfellow's work, but co-authored by Yoshua Bengio as well, right? And what are we talking about? So we are talking about GANs, which have two neural networks, G and D, generator and discriminator. And you can imagine this G to be very close to the second half of the encoder decoder that we talked about, it, where you're interpolating. You have a smaller dimensional Z and you get an image as output. And these images are fake images, right? These are not actually real images. Whereas you have a collection of real images, and the discriminator's job is to identify real data from fakes, right? Which is created by the generator. Whereas the goal of the generator is to turn noise into a sample which almost looks like it is coming from this original data distribution, right? And so this is another way of looking at the same thing. So you have X sample from data, and you have to learn a differentiable function D. D of X tries to be near 1, right? You want to put 1 for all real samples. Whereas samples which are generated by the generator, which is G, we would like to put, for those samples, we would like to put a 0, right? So you can discriminate between these two samples, and that's the goal of the generator, right? And so that is what is happening now, right? So we are able to learn both D as well as G so as to do this task, right? And with time, we will see that the generator is going to generate images which are more and more realistic, right? And people call this a min-max game that is being played between the generator and the discriminator. Okay, so another visualization just to help us get this across. So you have random data, you have a generator which shapes the distribution, and the goal of the generator is to get the distribution almost same as the real data's distribution, which is blue, right? And you have a discriminative network, which will try and distinguish the data coming from the generator and the data coming from the real data, right? And you have a back propagation that helps in getting the generator better and better, right? And so this is essentially what GAN is, right? And there has been a lot of activity in the GAN literature, both on the front of architecture. I mean, you see the architecture is basically the generator network, right? And a lot of interesting work that has happened in the architecture space, of course, application and so on, but also in the loss space, right? So here we are talking about comparing distributions. You could use KL divergence, JS divergence, and so on, right? So you can use several different types of comparing distributions, so particularly one work which is caught up a lot is this Wasserstein GAN, which is here, and you could also use several regularizers and WGAN GP, right? Gradient penalty on WGAN. This is also I mean, showing a lot of promising results. And why I'm saying this is we use in our work subsequently. Okay, so lots of work happened in this space after 2014, right, when the first model came out. And what has also happened from 2014 is that as you can see, the generator becomes more deeper and deeper, and what used to be fairly poor face images, which was in the beginning, now you're starting to get much more realistic images, right? And sometimes people joke saying, okay, what is the real, which one of the image is real in this, and so on, right? And all are fake. I mean, there is nothing that is real in this, right? And with the time, thanks to the idea of self-attention, which has come from text literature, where you go beyond the limitation of a CNN, which is only doing a local weighting, right? You can also look at a larger context using the self-attention GAN, and you starting to see very, very good images, right? In terms of quality as well as diversity. It's not that you're always generating one image and so on. So you have quite a bit of diversity as well, right? So this was about generating valid images, and we are getting better and better at that. At the same time, for problems that we might be interested in, we might also we might need to look at what are called conditional GANs, right? Conditional GANs take apart from the Z vector, which gives a randomness to the whole generation process. You can also take one input, right? So, for example, you could take the input as the edges, and once you have the edges, you can basically interpolate or paint or whatever you want to say, and generate this G of X, right? Which is an image that you're generating, and it's not an arbitrary image. It is basically there is a relationship between these two, which is what you want to capture, right? And maybe you have ground truth data where you have actual image and its edges, right, which are real, and you also generate fake data, right, from your generator, and those pairs are fake pairs, right? Where so these don't exist, right? These images don't exist. Maybe you can take one of the edges, but then edge images here and use it, but then these don't exist, right? And these are generated by the GAN, right? And these are what are called conditional GAN, which can be applied for a variety of problems, different types of input and different types of output, right? And an interesting line of work, which is called cycle GAN, extended it even further, right? Where they said instead of giving paired data like that, sometimes you may not have paired data for all the data that you want to do this mapping. You might have unpaired data where you have a folder of images, which could be a photograph folder, whereas this could be paintings coming from a painter, right? A famous painter, for example, Monet, and so on, right? So now if they use what is called a cycle GAN approach, where they not only do a mapping from photo to Monet, but also from Monet to photo, right? And if you start with some photo, you expect to come back to that photo, right? So this gives you a loss function, and you can train two networks, Monet to photo and photo to Monet. And tomorrow, given a new image, right, you can generate a new painting, right? Okay, so this is very interesting. So you can paintings. So machine has started to do painting, which is good. But we'll come back to our original task, which is the deblur GAN task, right? So as we just said, now we look at it from the conditional GAN point of view. You have these paired images, and you have the adversarial loss, where you have certain pairs which are valid, certain pairs which are generated by the network, and you use that adversarial loss. And we also, I mean, this work used a WGAN GP framework and produced high quality deblurred output, right? Very straightforward application of whatever we have seen so far, right? And where our work comes is, this is thanks to Saikat's work. So he's a Samsung student, and he proposed an ABCD GAN, right? So let's have our own GAN, attention-based cascaded deblur GAN, where it has two layers, right? So this is the original image, ground truth image. This is a blurred image. You take the blurred image as input, and you have two major networks. And the interesting thing here is we don't do this real or fake discriminator on this output here, but we do it only once, right here. So there are two losses here: the perceptual loss, which is taken care of more here, but not the adversarial loss. Whereas here, with this output, we take care of both the losses, right? And you can combine both the losses. So that's one novelty. The other novelty is to use the self-attention as well. So the previous works did not use self-attention. So now you can take care of long-range dependency as well, right? And here are some results: qualitative comparison, the blurred image, baselines, and then our approach, right? So these are qualitative results, and we also have quantitative results showing that the method does very well compared to other methods, right? And so we stop here. I mean, this work is just now completed, so we're writing it up, and now we will move on to conditional image generation to conditional video generation, right? So we produced images conditionally, which is good. Now we'll produce videos conditionally, right? And where it could be helpful, we would like to make this person dance, right? And this person doesn't know dance. So how do we do that, right? So this is a famous paper, which is Everybody Can Dance. And here you see that this one is completely generated by the neural network, right? And how does it work? So during training, right, what you do, you have frames, right? And for every frame, you can extract the pose, which is an analysis part, right? You have an image, you analyze, you get the joint location. And then you have a generator, which takes a joint location as input and produces an output, which is an image, right? And with the person there, right? And you tend to, you learn a generator for every person, right? And you can also learn such a generator for the person whose video we want to produce, right? And we can go from video to post to video, right? And once we have got this ready, now what we can do, we can transfer the pose of the expert onto this person and then generate new images, right? So our problem solved, right? And as you can see, there are, I mean, what this additionally compared to the images, what we are trying to do is we are trying to see if the frames are temporally coherent versus not coherent, right? For actual videos, it will be coherent, and you can learn the generator to also incorporate coherence, right? Not just producing valid images, valid people, but also temporally coherent, because we have a video that we are talking about, right? And additionally, the authors have also tried to model face much more closely, because you want to get the face neater, right? So they use a residual connection where apart from what exists from the first generator, you try to refine it further, right? And then you can put it back and say that this is a much refined face, right? Yeah, so this was very useful to get realistic looking faces, right? And in Rupak's MTech thesis, along with Kumar Shubham, an MS student, so we have explored the use of dense pose instead of joint location. We have used dense pose outputs, and we have tried to generate images, single images, and we have also tried to keep the identity of the person intact, right, compared to the image that you have, which is sort of the target image, right? So we want to keep the identity also fairly close, right? So this is what Rupak worked on. And another line of work, which is by Shashi, a Samsung student, was on trying to generate an animated video, right? So you have a person in the first frame, and you want to edit and create a video from this image where a person just comes out, right? And of course, I mean, it is not very difficult to imagine the pipeline. You have an image like this, you can extract the human foreground, you can create a segmentation mask, dilate it a little bit, and then do what is called an image in painting. You can create the background. And once you have created the background, what remains is to basically start from this pose and keep generating the subsequent post stick figures, and then generate the image of the person, right? Given whatever we have talked about, it's reasonable to imagine that, right? So now we can create videos as well. Okay, so here is a sort of a transition, right? Sort of midway we have talked about image, we have talked about video generation, conditional. Now we can start to talk about conditional text generation, right? And here again, we will take the approach where we will first talk about just pure text generation, which means that we should be able to generate paragraphs which make sense, right? And then we can talk about conditional text generation, which where we want to somehow steer this text generation to suit our need, right? Maybe it could be that we are trying to describe an image, right? We're trying to generate a caption for an image, right? So it's not any arbitrary text we want to generate, but we want to generate a caption for this image, right? Or we want to go further and say it's not just about caption, but a poem, right? We want to generate a poem for this image, right? And these are the conditional text generation tasks. Okay, so so let's start with text generation, right? So an early work on text generation was by Yoshua Bengio, whom we talked about, the neural language model, where you have a neural network where it can take, say, 2 words as input and produce an output distribution from where you can sample and pick a word, which could be a possible next word, right? And then you can keep doing this again and again, and this way you have generated a sentence, right? And as you can see, one of the limitation of this is, for example, here hardly ever, right? And you want to give as output believe or believes, right? Depending on whether it is a single person or plural, this will change, right? So you don't see what the subject is, right? So that motivated for people to say, okay, this neural network is not sufficient. You wanted a recurrent neural network, right? A recurrent neural network has this connection from the hidden state in the previous for the previous token and so on, and because of which you can remember what is the subject, right? And that information can flow across, right? And essentially what happens at every hidden node is basically a linear combination of the previous hidden states and a linear combination of the input at that particular token and a non-linearity, right? Which is a typical neural network. The only additional thing is you have memory, right? You get HT-1 as well. And while you give the output at every time instant, you have another matrix which takes a linear combination, and you can give an output. Maybe you take a softmax and you have a distribution over the vocabulary space, right? And as you can also see, we can use this model, which is a decoder model, right? Which can generate words, sentences. You can use it for image captioning, right? Where you can maybe take an image and use a CNN and get a vector, right, which summarizes that image, and you can make this do image captioning where you're generating a sentence which is a caption for this image, right? So this is already a conditional image generator. Whereas without this context, it would be a plain text generator. Now this context allows you to generate text which is conditioned. Okay, so we move from text generation to conditional text generation. Okay, now we can not just use image, you can also use this to do translation, right? So you have an encoder, which is exactly same as what you have in the decoder, the same operation that happen, right? Only thing is you don't have an output at the encoder level. You just have the hidden states moving from one token to the other, and then the final hidden vector, right, for the input given sentence in French, you have summarized and you got a vector here, and that is going as input as a context to the decoder. Now you can start to generate translation of this small phrase in French, right? So this was published in 2014, but then there is a limitation, as you can see, right? So this may not be very helpful in translating long sentences because you are summarizing everything that you have seen so far in this one hidden vector, right? And this was addressed in a 2015 work where the authors introduced an attention model, right? So how does the attention model work? So as you can see, the encoder is still the same. You have H1 to H5, and then you have a attention module here, right? And you have the decoder, right? And the decoder is generating, starting to generate words. And what is interesting here is the concept of attention, where instead of only depending on H5, now you can take a linear combination of H1 to H5, if you decide to only use H5, you give all the other weights 0, but you can also take combinations. You can jump and attend to some other words, hidden state, and so on. And this vector, which is coming from the previous hidden state of the decoder, it's called the query, and you have what are called keys, and you do a sort of a similarity matching, and whichever is more similar, you put the weightage for that as higher, right? And this way you can not just look at I mean the last hidden state. You can actually look at a very long sequence and take weightage of any needed hidden vector for that matter, right? And as you can see, you keep generating the words, but then you have full access to all the past, right? And you can take combinations. And this is nicely illustrated here, where you have a sentence in French and a sentence in English, and you see that the sort of linear sort of attention is broken here, and then you start to attend a word which is further away in French and produce the word European, right? And here is another visualization where you see that at the word zone, you attend to area and translate that, right? So this is a very very important idea. And I think one point which we can make here is compared to convolution, right? Where you take a weighted sum, the weights will depend on the position, right? So you have a kernel and you take a weighted sum, will depend on the position. Whereas here, the weighted sum depends on the similarity between the query and the keys, right? And so this is an important distinction, right? So you still do a weighting, but then the principle is slightly different, right? How you do the weighting, right? And for text, this seems to be an important idea, right? Okay, so we introduced the idea of attention, and this paper takes it further, right? And they say attention is all you need, right? And what are they saying? They are also saying that the RNN architecture that we saw, and subsequently RNN morphed into LSTMs, long short-term memory LSTMs, which is a gated network, right? So what they're saying is those are all gone, right? I mean, you don't need RNN and LSTM. What is the problem with RNN and LSTM? In a RNN or a LSTM, when you do the encoding, right, you have to wait till you finish processing the token that, say for example, for the 11th token, you have to finish processing the 10th token, then come to the 11th token, right? So there is a sequential nature that is a limitation of RNN and LSTM. And here they say, I mean, just use attention. And attentions are very good because they have lots of matrix multiplication, and you can do everything very quickly, right? And they introduce the transformer, right? You take, this is a short sentence, but then you can take a really long sentence as input and give as output a long sentence, right? Translate sentences. And because you can have this ability to handle long sentences, you can actually be very consistent, because you have taken in all the context of the input, and while generating output also, you can be the long range dependencies are well taken care of. Okay, so again, an advertisement for transformers, right? So Leo Dirac happens to be the grandson of the famous physicist, and he says LSTM is dead, or RNN is dead, long live transformers, right? And from now on, I mean, transformers is the main story, right? So what are transformers? As you can see, you have an encoder decoder. I mean, several encoders stacked up, several decoders stacked up, right? And you take as input say a 70-word sentence, and give as output another sentence of a similar length, right, in a different language, right? And when you look at what is inside an encoder, right, it has a feed forward connection and a self-attention, which is a self-attention network, let's call it, right? And in the decoder also you have a feed forward self attention, but also a encoder decoder attention, right? So if you go back and look at the example we saw where we had attention in a LSTM network, right? There we are essentially doing this decoder encoder attention, right? For every decoder position we are looking at the encoder and attending to the encoder hidden states, right? So similarly we can do something like that here as well. We could also do self attention both at the encoder and decoder. So maybe if you're translating from French to English, so this self attention would be all about attending to other words in a sentence in English. Here it would be in French, right? And just to sort of clarify a little bit, so the feed forward connection here is separate for every word, right? And you just reuse, you can reuse the weights if you wish, and here so these are separate, whereas here is where the interesting thing happens, right? So so this is for every word a separate processing that happens, whereas here you are attending for every location. You will be attending at all other words in a 70 word sentence, right? And then you will be computing what this vector should be, right? And I mean, it's a little bit of detail for this talk, but again there is this notion of query, key, and value, and you end up computing what the z is, right? And these are extremely I mean, operations which can be easily done in a GPU, right? Because these are matrix operations primarily, right? And another innovation in the transformer paper was this notion of multi-headed attention, right? So here you see, if you just focus on the word it, right? And it refers to the animal, right? And that's why you see there's a lot of attention that is going to the animal. And so this could be one head, right? One set of weights. And you have multi-headed attention where for different meanings, say conjugation, gender, and so on. So you could actually have multi-heads which attend to different things which are of interest, possible interest that you would like to encode for a particular word, right? And as we said, it's all highly parallelizable matrix operations. Okay, so far so good. So what we have managed to do, we have managed to build the elephant, right? And so this figure is credit to a later work that we will talk about. So we have built an elephant, and this elephant is essentially the decoder side, which is also called the generative pre-trained transformer. Maybe it is trained on Wikipedia, and it comes in all sizes, right? Small, medium, and large. For us, maybe for our lab systems, small is good enough. We can't even think of medium or large at this point, right? So they're really large number of parameters. And here is one example sentence that is coherently being generated by this decoder using the GPT transformer. There is GPT, and then there is GPT-2, right? And this is one such version, let's say. And this is a language model, right? What can a language model do? If you give few words, it'll start generating the subsequent word, right? And you can generate a sentence. Okay. And an interesting work which was along the lines of conditioned text generation. So the previous one is just a pure text generator. Now we want to condition it, maybe use it in an application. So we need to tell this elephant, I mean, now it knows to walk, but maybe you have to put a road, right? And say, okay, walk on the road types, right? So how do you fine tune GPT-2 so as to solve a particular application problem? So this is a interesting work, transfer, where they said this is the knowledge which we have, which is about a person. There is a personality, and can you use this knowledge to generate chat responses, right? Text chat, and you'd like to generate text responses. If you just use GPT-2, maybe it won't be sort of fine-tuned or will not reflect this personality, right? Now you would like to add this additional constraint and bring in this personality, right? And what they had shown was, I mean, if you could fine-tune using a separate data set which has this property. And then you could also use the dialogue history and be able to generate interesting chat responses, right? Benefit from the fact that they have a smaller but very domain specific data set, right? And this is an open problem, right? You would like to adapt to a particular domain, right? Okay, so far so good. And what we did in our work is we tried to adapt this transfer to the problem at hand, which is to be able to generate responses from a interviewer. The interviewer has asked a question, the candidate has replied, and then we want to ask a follow-up question, right? And so just in the same spirit as we talked about in the previous work, here credit to Pooja and Manish, we have a sort of a real-time interviewing system where you can ask a follow-up question, right? And the task is to generate F, given Q and R as input. You can train. So we did have a data set which we collected, and so using that data set where we have follow-up questions for 1089 triples, we added along with the language modeling loss, which is a next word prediction loss. We also added a next sentence classification loss, because we have these triples, right? We can create a task where there is a valid follow-up sentence and a sentence which is not valid, a random sentence. You can create a classification loss with that, and given that you can train this model with these three alongside question, response, and a follow-up using this data set, we were able to train a model, right? And we will be able to ask the follow-up question, right? Okay, so this work is accepted in ECAI Intelligent Language Workshop 2020. And here you can see examples where these are generated follow-ups, text generation, conditioned on the question and the response, right? And these are with text input. We also tried with speech input, where you also do automatic speech recognition, right? And the responses generated follow-ups makes sense. They can be better. I mean, it's not that they are the best, but they do make sense, right? And you can have applications where you want to have some amount of unscripted component, and this is really good, unscripted. And also sometimes you want to ask questions. You want to ask questions where the candidate may not be prepared, right? It's a slightly off. I mean, the question is a little off, and you'd like to get a response from the candidate. Okay, so far so good. So we have the interviewer ready, right? And now let's go to the poet, right? So how do we use this to create a poet, right? And this is a work from Uber, very recent work, which is a plug and play language model, where they propose to control this elephant using a mouse. So elephant is large, mouse is small, less number of parameters, but then the mouse can help you help the elephant navigate, right? Through its gradients, it can navigate, help the elephant navigate, right? And so essentially they use this Bayes theorem principle, where you have the language model, which is unconditioned text generation model, and then P of x given A, which is a conditional text generation, and P of A given x is an attribute model. And one sort of intuition, as you can see, these are contours where the P of x is having same value, and you would take a first step which is along the direction of ascending on the attribute space, right? And then you would ascend on P of x, and you would reach this point, which is better than this location, right? And you can also see these are the red curves correspond to P of x being lower to higher. So you have reached a point where according to the attributes, it is better, right? At the same time, it's not very far in terms of P of x. It's still similar P of x, right? The language model is still having the same cost, right? So how can this be helpful? So this can be helpful, for example, if you want to generate a positive sentiment, right? You have generated chicken taste, which is from a base language model. Now you have this option of saying that, okay, I have an attribute model which wants to generate positive sentiment. Now you can on a runtime basis, you can start to generate delicious. Otherwise, you would have generated okay, right? Chicken tastes okay. Whereas now you generate delicious. Okay. So another example, you can generate sentences which are having a particular topic. The issue focused, right? That's the starting sentence. This is a plain GPT-2 output. Whereas now you can have attribute model which is trained for different topics, right? Now you can start to generate sentences which are focused on military, politics, science, and so on, right? So this is one of the application is you can increase the proportion of topic in the sentence you generate, or you can also use it in a very interesting way, which is one of the application. You can also remove the toxicity, right? Suppose you're generating some sort of you just want to reduce the probability that toxic speech is produced, right? So you can just take the opposite direction, right? Instead of increasing the toxicity, you can decrease the toxicity, right? Which is the same principle. Whereas we have tried to use it in our application, which is for poetry generation. So you have a image for people who are nostalgic about IIIT. Here is a image of a IIIT, and you have a caption. Maybe the caption could come from the condition, the image generation that we talked about, a building with grass and trees. And you have the model, which is, this is a work by Abhiraman, right? So PPLM, which we talked about before, and we also have a rhyming element to it. We'll come to it subsequently. And we are able to generate a sentence like this: a building in a garden of trees and grass on the walled-in floor, a small and humble building. Its walls were made of glass and the roof creaked and cracked with the rain, right? So a question is, okay, how did we bring about this rhyming aspect, right? And another such output. So here you have a flower image as input, and the way all these models work is you have given an image, you have a caption, you start the poem with the caption, but then you ignore it later. You use a language model and generate say 50 tokens, and then you also ignore the last sentence, right? And what we benefited from thanks to Abhiraman's work was we had data sets which were poetry data sets, right? And we could fine tune the GPT-2 model to those poetry data sets, which is why you are seeing not paragraphs, but you're starting to see poems. May not be best to start with, but then as you can see, once we bring in the transfo idea, which we talked about before, fine tuning. So we did have one data set, which is an image poem pair data set, data set. So we use that, right? We use that to get much more sort of relevance to the image that we have, right? And at PPLM, for PPLM, we added this additional aspect, which is, so as you see, you have the attribute of the topic, right? And there is what is a bag of words from which you can steer the language model to use those words, right? And as long as we are able to runtime add rhyming words into the vocabulary, you will start to see that those words are getting used, right? And the poem starts to rhyme as well, right? And so that is what we did. And we also did a comparison with these three models and several evaluation metrics. And we could see that at least in the rhyme and relevance, we have very good performance with the PPL and rhyme. And it's also not bad on the other metrics, but still there is scope for improvement. Okay. So here's the last slide. So if you ask, can machines paint, write poems, and interview people? Yes. Are they perfect? Not yet. I would only say it's exciting times ahead, and acknowledgement to students, funding fees, and I stop here.
Thank you, Dinesh. That was exciting. A big round of applause for you. Yeah, so there are a few questions here, and there are a few raised hands as well. So shall we get cracking with them?
Okay.
Admin has asked how is the decoder trained to read Wikipedia and are DSP filters used in deep blurred images?
So I'll try to answer, Jaya. So the decoder trained on Wikipedia is, I mean, it's a, I mean, so you have text, right, from Wikipedia, which are sentences, and if you can use a language modeling loss, which is to predict the next word, you can train the decoder to be able to produce sentences in Wikipedia. Of course, reading Wikipedia is to be able to encode every word using some sort of embedding into a number, right? So I think that should be fine, I think. Are DSP filters used in deep blurred images? No. So these are not DSP filters. These are learned filters, right? So these are learned from the training data. Okay. How is the reliability assessed? So in the case of deblurring, we do have um, peak SNR and as well as SSIM metrics, right? And those were the metrics that are commonly used to assess the reliability of the blurring, deblurring. So Rachel is asking, do you think self-attention can replace convolutional nets, or is the complexity too high? I think, I mean, slowly self-attention is becoming an important concept even in image literature. And there is a very recent work from Microsoft, which is on image super resolution, and they are using self-attention there, right? And several works are still cross-pollination, I think.
Dinesh, what are the programming languages best suited?
So I think for these PyTorch and TensorFlow, so we do have existing libraries which we can benefit from. Yeah.
Okay, and resources on machine learning? Where can one find resources?
On machine learning, that's a so there is, I mean, if there is an authority in terms of deep learning, so there is a textbook by Yoshua Bengio and others, a textbook on deep learning. That's a very good source. But for the rest of the talk, these are all publications, right? So primarily publications. Yeah. Yeah, GPT-2 is open source. You can look at Hugging Face. Is a good source.
There are a few more questions, Dinesh.
So what
Prafra,
length of, what is the length of the text and so on? So for the self-attention, you can look at it as something like 70 words, so which is much more than a sentence and close to a small paragraph. Yeah. Yes. So computational power. I mean, so for training from scratch, so we should forget it. I think that's the game of big boys, Facebook, Google, and so on. But we can only fine tune or use them like in the attribute model and so on. But training from scratch is a different story. Thanks everyone for attending. So happy that you all have some takeaway.